In this video we will be going over rational functions. What a rational function is, simply put, it's when we have a polynomial divided by another polynomial. Okay, something like this, n of x over d of x, where each of these are polynomials. So a few examples of rational polynomials. We could have 3x squared divided by x minus 1. We have two polynomials getting divided. We could have something like this, 5x squared minus 25 divided by x. H of x equal to, let's say, 3x squared minus 1. Now this one doesn't look like we're dividing two polynomials, but really this is the same thing as 3x squared minus 1 getting divided by some constant, namely 1. 1 is a polynomial. It's just a constant polynomial. So all three of these are rational functions. Now in this video we're specifically going to be going over how to graph rational functions. And to do that we need to discuss asymptotes. The first asymptote to cover is a vertical asymptote. And a vertical asymptote is simply what values make the denominator 0. So we would say these are the unique zeros of the denominator. Now, every rational function will not necessarily have a vertical asymptote, but many of them will. And so, for example, if I have this function, f of x, let's say x squared minus x minus 12, and then in the denominator we have x minus 4. Actually, let's say x minus 1 here. Well, the value that's going to make the denominator 0, well, this will equal 0 when x equals 1. So we would say that x equals 1 is the vertical asymptote here. Now what we mean by unique zeros, let's come up with a second rational function. Let's keep that same denominator, and now let's make, or the same numerator, and let's make the denominator x minus 4. Well, if we factor the numerator, we're going to have x minus 4, x plus 3, and then in the denominator we have x minus 4. Well, what happens is because x minus 4 is a common factor, it cancels. So we don't say that x equals 4 is not a vertical asymptote. What we would say is there's a hole in the graph at x equal to 4. So when we input 4 into this function, so g of 4, we would get something that's undefined, because in the denominator, if we input 4, we're going to have 0 in the denominator. But because x minus 4 is not a unique 0, we don't say it's a vertical asymptote. We say that there's a hole in the graph at x equals 4. The next asymptotes to go through are horizontal asymptotes. And to find horizontal asymptotes, we compare the degree of the numerator and the denominator. We're going to say the numerator is n of x, the denominator is d of x. So there's three possibilities. The first possibility is the degree of n of x is equal to the degree of d of x. Just say d of x here. So if the degree is equal in the numerator and the denominator, we say that the coefficients determine the asymptote, so determine the horizontal asymptote. So that's the first instance. The second instance is if the degree of the numerator is less than the degree of the denominator. And if that is the case, we say that y equals 0 is the horizontal asymptote. And then the third instance is if the degree of the numerator is greater than the degree of the denominator. And if we have this, we would say that there is no horizontal asymptote. No horizontal asymptote. So that covers the three instances, and later in the video we will do a few examples, and each of these will be addressed. The third and final type of asymptote is an oblique asymptote or a slant asymptote. If the degree of the numerator is exactly 1 greater than the degree of the denominator, then the function has an oblique asymptote. And how we find this is we divide n of x, or the numerator, by d of x to find the oblique asymptote. And again, we will check out an example of this when this occurs. One thing to mention about oblique and horizontal asymptotes are that if we have a rational function, the function will have, or the function cannot have both oblique and horizontal asymptotes. So the result of this is that if we have a rational function and we're trying to graph it, and we find that the function has a horizontal asymptote, we don't even need to consider whether there's an oblique asymptote or not. So that kind of narrows down the procedure for us. So here are the steps that we would follow to graph a rational function. First thing we want to do is find the domain, and this corresponds to the vertical asymptotes, because remember, the vertical asymptote, or asymptotes if there's more than one, how we find that is by figuring out what value makes the denominator 0, and this will correspond to the domain. So the domain and the vertical asymptotes kind of go together. Then we find any horizontal or oblique asymptotes, and remember, we cannot have both, so if there's a horizontal asymptote, there is no oblique asymptote. And then we find the zeros for the function. What we do to find the zeros is set the numerator equal to 0 and solve. This will tell us when the function is equal to 0. Then we find find the y-intercept. The y-intercept, we can find that by evaluating f of 0, and then test a few different points to determine what the graph is. So these are the steps we will follow in the next examples. So let's look at some examples here. The first one asks us to find let's look at a few examples here. The first one says, for the function, find all asymptotes, the domain, x and y-intercepts, and then graph. Now when we're going through this, it's a good idea to always factor the top and the bottom. So if I factor out 2, I'll do this step by step. Factor out 2, I'm left with x squared minus 1 over the denominator is a difference of squares, so x plus 3, x minus 3. And then in the numerator, I still have a difference of squares, so this will be 2 times x plus 1, x minus 1, and then in the denominator, x plus 3, x minus 3. Now there's 2 reasons we want to factor here. One, we want to see if any of the factors cancel in the numerator and the denominator. In this example, no factors will cancel. This also shows us quickly what values will make the denominator 0. So let's find the domain. The domain is going to be anything that makes the denominator equal to 0. So the domain is going to be everything except for 3 and negative 3. So we could say all x such that x does not equal 3 or negative 3. That's in set notation. We could also write that in interval notation. Vertical asymptote. The vertical asymptote corresponds to what the domain is. The vertical asymptote, remember, is whatever values make the denominator equal to 0, as long as we don't have any factors that cancel out. So all of the factors in the denominator are unique. So the vertical asymptotes are going to be x is equal to 3, x is equal to negative 3. So those are vertical lines. For the horizontal asymptote, because the degree of the numerator and the degree of the denominator are both 2, we just look at the leading coefficients of the numerator and the denominator. So the leading coefficient of the numerator is 2, the leading coefficient of the denominator is 1. So we would say the horizontal asymptote is 2 over 1, or just y equals 2 here. Because there's a horizontal asymptote, that means there is no oblique asymptote. Remember, we cannot have both a horizontal and an oblique asymptote. For the x-intercept, what we do is we set the numerator. We want to find out when does the numerator equal 0. So if we factor this, which we've already done, we're going to see that x is equal to 1, x is equal to -1. So we want to write these x-intercepts as ordered pairs. So we would say 1, 0, and -1, 0. Those are going to be the x-intercepts. And then for the y-intercept, I'll do it down here. For the y-intercept, we evaluate f at 0. So we input 0. And when we do that, we're going to get -2 over -9, which is 2/9. So the y-intercept is going to be 0, 2/9 here. So to graph, we just put all of this info together. Let's plot in the asymptotes. So we're going to have an asymptote at +3, -3 for the vertical asymptotes. And then -3. And then a horizontal asymptote of 2. So this will be up here. And then I'll do the graph in red. No oblique asymptote. The x-intercept, we're going to have 1 and -1. And then the y-intercept is 2/9, so that's something like right here. So when we're going through the graph, we are never going to cross a vertical asymptote, but we could cross a horizontal asymptote. Well, this graph in here, it's going to come down like this. Now, because this is a function, this graph will pass the vertical line test. So what that means is we're not going to have any graph up here, because if any part of the graph is in this region, it will not pass the vertical line test. So we need to figure out, is the graph going to be up here or down here? And then similarly, is the graph going to be here or here? So above or below that horizontal asymptote. So let's see how we can determine that. What we want to do is just pick a few points and see what happens. So I'll make a little table here. So if we plug in, let's say that point is going to be 4 there. When we plug in 4 into the function, we're going to get 30 over 7, which is a little more than 4. So that's, what, 4 2/7? So what that tells us is when we plug in 4 into the value of the function, we're going to get a point somewhere up here. Now what that tells us is that this graph must be in this section. And what the asymptotes tell us is as the curve either goes towards positive infinity or negative infinity, it gets really close to those asymptotes. So as the x values increase, this curve right here is going to get really close to that horizontal asymptote. Similarly, as the x values get really close to +3, this curve is getting really close to that vertical asymptote of 3. Now similarly, we want to be on the left side of, we want to know again whether the graph is going to be up here or down here. So all we need to do is pick an x value that is to the left of that vertical asymptote. So how about -4? And when we plug in -4, we're going to get the same value, 4 2/7. 4 2/7 is above that horizontal asymptote, something like here. And again, the curve is going to get very close to those asymptotes in our end behavior. So that's what the graph is going to look like. Okay, the directions are the same for this example. We have f of x equals x plus 2 over x squared minus 4. Again, let's factor the numerator and the denominator. Well, can't factor the numerator. The denominator is going to be x plus 2 x minus 2. And what we have here is we have a repeated factor in the numerator and the denominator. So this function that we're going to work off of is 1 over x minus 2. Okay, so let's find the domain. The domain is going to be anything that makes the denominator 0. Well, 2 and negative 2 would make the denominator of this original function 0. So we're going to say all x such that x does not equal 2 or negative 2. For the vertical asymptotes, here we need to think, what are the unique factors of the denominator? And we only have one unique factor of the denominator, and that's x minus 2. So the vertical asymptote corresponds to that unique factor. We're going to say x is equal to 2. And the factor that cancels out x plus 2, well, that corresponds to a hole in the graph. So we're going to say there's a hole in the graph at x equals negative 2. And when we get to the actually graphing this, we'll see what that looks like. For the horizontal asymptote, again, compare the degree of the numerator and the denominator. The degree of the numerator is 1. The degree of the denominator is 2. So when the degree of the numerator is less than the degree of the denominator, we always have the line y equals 0 as the horizontal asymptote. So this tells us there is no oblique asymptote. And then for the x-intercept, we want to determine when the numerator is equal to 0. So we're going to say x is equal to negative 2. So writing that as an ordered pair, we're going to say negative 2 comma 0. To find the x-intercept, we want to set the numerator equal to 0. So x plus 2 is equal to 0. This is going to tell us that we have an x-intercept at negative 2. However, this is when there's a hole in the graph. So we have a hole in the graph when x is equal to negative 2. So again, what this is telling us is that the function is undefined when x is equal to negative 2. So we're going to say that there is no x-intercept. And then for the y-intercept, we input 0 into the function. So f of 0, we're going to have positive 2 over negative 4, which is negative 1/2. So the y-intercept is going to be 0 comma negative 1/2 here. And now let's put this all together and come up with the graph. Okay, so vertical asymptote at x equals 2. We have a horizontal asymptote at y is equal to 0. So right along the x-axis. And then the only point that we know so far is this y-intercept, and that's at 0, negative 1/2. So right here is where the y-intercept is. Now, because we are below this horizontal axis, or the horizontal asymptote, we know that the graph is going to approach that horizontal asymptote, then it's going to come down here and approach this vertical asymptote. And then looking at where the hole on the graph is, the hole is at negative 2. So what that tells us is that at negative 2, we're going to put a hole in the graph. So how can I show this? We would put a hole in the graph, something like that. That's how we can do it. We could label it something like this. Okay. Now we want to figure out what's happening to the right of this vertical asymptote. So again, what we're going to do is pick an x value. How about x is equal to 3? And let's plug that into the function and see what we get. So when x is 3, we're going to get 5 over 3 squared is 9 minus 4 is 5. So that's equal to 1. So at 3, we're going to have an x, or we're going to have a y value of 1. So we're up here. So that tells us the graph is above, kind of in this quarter of the graph. And there we have it. Okay, one more example. Again, let's factor the numerator and the denominator. The numerator is x plus 2, x minus 2. The denominator is just x plus 1, already factored. So no factors cancel here. Let's go ahead and find the domain. The domain is going to be whenever x is equal to -1. So all x such that x does not equal -1 here. For the vertical asymptote corresponds to any 0 of the denominator that is not also a 0 of the numerator. So we're going to say x is x is equal to -1. That's our vertical asymptote. That's our equation of the vertical line. And again, it corresponds to what we have in the domain. Horizontal asymptote, well, because the numerator is greater than the denominator, we do not have a horizontal asymptote. Now, because there is no horizontal asymptote, this means there may be an oblique asymptote. And remember, an oblique asymptote occurs when the numerator has a degree that is 1 greater than the denominator. And we have that. The numerator is degree 1, or degree 2, the denominator is degree 1, so the numerator is 1 degree greater. So what we do is we divide. So what we want to do here is divide x squared minus 4 divided by, I can write a better division sign, divided by x plus 1. So we could do long division here. However, because the divisor is linear, we could divide this using synthetic division. So I have -1 in the divisor, and then I write the coefficients of the dividend. So I have 1 x squared. I'm missing the x term, so I'm going to write 0 for the x term, and then -4. So recall that we bring the 1 down. 1 times -1 is -1. And then we're adding 0 plus -1 is -1. -1 times -1 is 1. -4 plus 1 is -3. Now, it doesn't really matter what we get here. That's just a -3. What we want is that 1 is going to become x, and then we're going to have x minus 1 here. And that is our equation of our oblique asymptote. So it's the equation of a line. So this is a line with a slope of 1 and a y-intercept of -1. All right. We need to find x and y-intercepts. So x-intercept, we want to set the numerator equal to 0 and solve. The numerator is going to be 0 at -2 and 2. So we'll have -2 comma 0, and then we'll have 2 comma 0 as the x-intercepts. For the y-intercept, remember, we want to find f of 0. So when I plug in 0 into this function, I get -4 over 1. So this is going to be 0 comma -4. And putting everything together, we have a vertical asymptote of x is equal to -1. So there is our vertical asymptote. There's no horizontal asymptote, but the slant asymptote is y equals x minus 1. So that's telling us we have a slope of 1 and we're crossing at y equals -1. So our slant asymptote is going to look something like this. We have a y-intercept of 0, -4, so that's somewhere down here. And then we have x-intercepts at 2, 0, and -2, 0. Okay, so looking at the bottom right section of this graph, well, I have 2 points in that section, and we're going to connect those points. What's going to happen is we're going to go along that slant asymptote and then start going in the towards -infinity along the y-axis. So we are approaching that vertical asymptote, and then because I have this section of the graph in the bottom right portion here, that tells me I have no graph in this upper section, because if I did, that function would not pass the vertical line test. We know also that the graph is over here because we have that x-intercept. So the graph is going to come down like this. So those are the 2 parts of this graph.